So let's draw a picture of the graph of y equals a to the x using our techniques of graphing developed in Calculus 1. We're going to get a different graph for the different values of a, so we're going to split the analysis into two cases. The family of functions y equals a to the x when a is between 0 and 1 will slope downwards, and we'll treat the graphs of those separately from the graphs of the family of functions y equals a to the x when a is larger than 1, which slope upwards. So let's look at the graphs of y equals a to the x when a is between 0 and 1. I've drawn some here. Y equals 1/2 to the x, y equals 1/4 to the x, y equals 1/8 to the x, and of course y equals 1 to the x, which is just the graph of the function y equals 1, which is just a horizontal line. Let's look at the intercept, the y-intercept of y equals a to the x. So this is where x equals 0, and we have the y value as a to the 0, which by definition is e to the 0 times the natural log of a, which is e to the 0, which is 1. What about the x-intercept? Well, this is where the function crosses the x-axis, so the y value is 0. So it crosses at the value of x where a to the x equals 0. But a to the x is e to the x times the natural log of a, and e to any power is always positive, so there is no such x, and there is no x-intercept. What about the slope? Well, I can figure that out by differentiating the function. The derivative with respect to x of a to the x is a to the x times the natural log of a. Now, if a is between 0 and 1, the natural log of a is negative, and the graph is sloping downwards as I move from left to right from minus infinity to infinity. In this case, a smaller value of a is going to give me a steeper curve, as you can see from the three graphs that I've drawn here. The graph is also concave up because if I calculate the second derivative, which is the derivative of the first derivative, I get the natural log of a times the derivative of a to the x, which is the natural log of a squared times a to the x. And this is always positive because it's the product of two positive numbers, therefore our graph is concave up. As x approaches infinity, x times the natural log of a is negative, but increasing without bound, so it's approaching negative infinity. And therefore, a to the x, which is e to the x times the natural log of a, approaches 0. And as x approaches negative infinity, x times the natural log of a is positive because it's the product of two negative numbers. Therefore, this approaches plus infinity, and therefore a to the x, which is e to the x times the natural log of a, is e to a positive power where the power is growing without bound, and that approaches infinity. So we get two new limits. The limit as x tends to infinity of a to the x when a is between 0 and 1 is 0, and the limit as x approaches negative infinity of a to the x when a is between 0 and 1 is infinity. And this is evident on the graphs I've shown on the left. What about when a is bigger than 1? Well, again, we can run through the application of our tools from Calc 1. The y-intercept is the y value when x is 0, so y equals a to the 0, which equals 1. So no matter what a is, the y-intercept of the graph, y equals a to the x, is 1. Once again, the x-intercept doesn't exist because there is no solution to the equation a to the x equals 0. If a is bigger than 1, And the graph of y equals a to the x has a positive slope because a to the x times the natural log of a is positive because the natural log of a itself is positive. And therefore the graph is increasing as we move from minus infinity to infinity. Graph is still concave up because the second derivative is a to the x times the natural log of a squared, which is also positive. And in this case, a larger value of a is going to give me a steeper curve. As you can see from the three curves I've drawn here, y equals 2 to the x, y equals 4 to the x, and y equals 8 to the x. As x approaches infinity, x times the natural log of a approaches infinity because the natural log of a is positive, and therefore a to the x, which is e to the x times the natural log of a, also approaches infinity. And as x approaches negative infinity, x times the natural log of a is negative, and therefore a to the x, which is e to the x times the natural log of a, tends to 0. So once again we have two new limits, which are the reverse of our previous limits. For a bigger than 1, the limit as x tends to infinity of a to the x is infinity, and the limit as x tends to minus infinity of a to the x is 0. And we can see this reflected on the graphs on the left, where a is 2, 4, and 8 respectively. Now we have 4 different types of functions involving bases and powers, and we have all of the tools we need to differentiate each one, but I just want to recap on how you might approach the 4 different types. If a and b are constants and g of x is some function which is always greater than 0, and f of x and g of x are both differentiable, then if I were asked to differentiate a to the b, because this is a constant function, the a and the b are not changing as x changes, its derivative is 0. If I were asked to differentiate f of x to the power of b, then I would use the chain rule. This is just a composition of two functions. First I apply f, and then I raise it to the power of b. So I differentiate with respect to f of x first, and then multiply by the derivative of f of x. And I get b times f of x to the b minus 1 times f prime of x. If I were asked to differentiate a constant a to the power of some function g, I would use the chain rule in conjunction with the derivative of a to the x, or convert it to e to the g of x times the natural log of a, and use the chain rule for e to the x. So I would get e to the g of x times the natural log of a, which is just a to the g of x, times the derivative of g of x times the natural log of a, which is the natural log of a times g prime of x. So I would get this expression on the right as the derivative. And lastly, to differentiate f of x to the g of x, I might write it as e to the g of x times the natural log of f of x, and use the chain rule for e to the x, as I've just done for a to the g of x. Or I could use logarithmic differentiation. We'll look at an example in a second of where I use that. Also, to calculate limits of functions of this type, of the type f of x to the g of x, it helps an awful lot to write it as e to the g of x times the natural log of f of x. Let's look at an example. Suppose I want to differentiate x to the 2x squared, where x is greater than 0, so this is well defined. We can use logarithmic differentiation on y equals x to the 2x squared. So we apply the natural logarithm to both sides. We get the natural log of y is 2x squared times the natural log of x. Differentiate the left-hand side, I get 1 over y dy dx. When I differentiate the right-hand side using the product rule, I get 4x times the natural log of x plus 2x. Now multiplying both sides by y, I get dy dx is y times 4x times the natural log of x plus 2x, and then converting the y back to x values, I get my derivative is x to the 2x squared times 4x times the natural log of x plus 2x. Let's try to solve this limit. As I mentioned, it helps an awful lot to write this as the limit as x goes to infinity of e to the minus x times the natural log of x. That's just using the definition of x to the minus x. And now as x approaches infinity, the x value approaches infinity, and the natural log of x also approaches infinity. So minus x times the natural log of x approaches negative infinity as x approaches infinity. Using that, we can convert our limit to the limit as u approaches negative infinity of e to the u, and now I know immediately that that is equal to 0.